Okay, hi everyone. In the last class we discussed Raman spectra. Now we discuss some important concepts from NMR spectroscopy. Nuclear magnetic resonance spectroscopy. Nuclear magnetic resonance spectroscopy. So the name itself indicates NMR spectroscopy is nothing but it is the study of interaction of radio frequency radiation. Here which radiation we use? Radio frequency radiation we use. It is the study of interaction of frequency radiation with various nuclei present in the sample molecule, with various nuclei in the presence of magnetic field. In the presence of magnetic field. That's why it is to be nuclear magnetic resonance spectroscopy. So in the presence of magnetic field, we are studying the interaction between nuclei and radio frequency radiation. Okay. So what is the role of magnetic field? We'll see later. So here we are studying the interaction between what? Radio frequency radiation and nuclei. So whenever we are applying radio frequency radiation, what happens? Whenever we are applying radio frequency radiation, what happens? This radio frequency radiation energy is very, very small. That energy is not sufficient for rotational transitions or vibrational transitions or electronic transitions. That radiation is not sufficient. Its energy is very, very low. That energy is sufficient only for transitions between nuclear spin energy levels. The transitions occur between what? Nuclear spin energy levels or inversion of nuclear spin takes place. Inversion of nuclear spin takes place. Nuclear spin will be changed during transition while we are applying radio frequency radiation. So therefore in NMR spectroscopy, nuclear spin is important. Okay, in NMR spectroscopy, which is important? Nuclear spin is important. So nucleus is important. Nucleus. Okay, here we are studying the interaction of radio frequency radiation and nucleus. So that's why nucleus is important. So we know nucleus possesses both protons and neutrons. Nucleus has the property of spinning. Nucleus has the property of spinning, so therefore it possesses intrinsic spin angular momentum. Nucleus possesses spin angular momentum. So similar to orbital angular momentum or electron spin angular momentum, nuclear spin angular momentum is given as, I am indicating with I, okay, with the thick line I am indicating, this is a nuclear spin angular momentum. So that is given as I into I plus 1 h by 2 pi r h bar, where I is called as nuclear spin quantum number. Nuclear spin quantum number. Okay, this is spin angular momentum of nucleus. Okay. Now nucleus is a charged particle or not? Yes, nucleus possesses charge, positive charge. It is a charged particle. Whenever a charged particle is under spinning, it produces some magnetic field. Whenever a charged particle is under spinning, it produces a magnetic field similar to electron. Electron also charged particle, it also produces magnetic field. Electron behaves like a teeny magnet. So it also produces magnetic field. So it also possesses what? Magnetic momentum. So nucleus also possesses magnetic momentum. So the magnetic momentum of nucleus is given by this formula, just to remember, G mu n square root of I into I plus 1, where G is called as nucleus G factor or splitting factor, and there is some constant that depends on the nature of nucleus. So that is called as nucleus G factor or splitting factor. Mu n is called as nucleus Bohr magneton. Nucleus Bohr magneton. So this is some basic unit we follow to express magnetic momentum. Okay, nucleus possesses both spin angular momentum and magnetic momentum. This is the formula for spin angular momentum. This is the expression for magnetic momentum. So to express magnetic momentum, generally we follow this basic unit. Bohr magneton is some basic unit to express magnetic momentum. The expression for Bohr magneton is EH by 4 pi mp. EH by 4 pi mp. Okay, is the charge H Planck's constant, 4 constant, pi constant, m mass of the proton. Okay, so here we will get to take proton. EH bar by, that can be written as EH bar by 2 mp. H by 2 pi we can write as what? H bar, reduced Planck's constant. So that is the expression for Bohr magneton. Okay, and we know spin angular momentum is a vector quantity. Magnetic momentum is also a vector quantity. So it has 3 components: mu x, mu y, mu z. It has 3 components: mu x, mu y, mu z. So mu z, z component magnetic momentum is given as G mu n mi. G mu n mi, where mi is called as magnetic spin quantum number. Magnetic spin quantum number. This is similar to L and ML. L is azimuthal quantum number, ML is magnetic quantum number. Okay, this is in the absence of magnetic field, this is in the presence of magnetic field. Similarly, here also we have I and mi, nuclear spin quantum number. This is magnetic spin quantum number of nucleus, magnetic spin quantum number of nucleus. In the presence of magnetic field, one level may split into various levels. Those various levels are distinguished by using mi. So this is the what? Z component magnetic momentum. Okay, G mu n mu I. Okay, and here if you see, mu is equal to, we have G mu n we can write as EH bar by 2 mp square root of I into I plus 1. EH bar by 2 mp square root of I into I plus 1. Square root of I into I plus 1 into H bar, that is nothing but what? This is nothing but what? Spin angular momentum. Okay, that is nothing but spin angular momentum of nucleus. So therefore mu is equal to GE by 2 mp into spin angular momentum. I am indicating like this with a thick line. So here GE by 2 mp we are getting mu by I. Mu by I we are getting GE by 2 mp. This is called as GE by 2 mp, or the ratio of magnetic momentum to spin angular momentum. That is called as gyromagnetic ratio, gamma. That is indicated with gamma. That is called as gyromagnetic ratio or magnetic gyro ratio. Magnetic gyro ratio. So magnetic gyro ratio is nothing but what? That is the ratio of magnetic momentum to spin angular momentum of the nucleus. Just you possess some idea on this terminology. Okay. In CSI type of exams, they are giving questions from these concepts also. Okay. So nucleus has the property of spinning, so it possesses spin angular momentum. Whenever charged particle is under spinning, it produces magnetic field, so it possesses magnetic momentum also. This is the magnetic momentum. The ratio of magnetic momentum to spin angular momentum, that is called as gyromagnetic ratio. The expression for gyromagnetic ratio is GE by 2 mp or mu by I. Okay. Next one. Nuclear spin quantum number. Here, how to get nuclear spin quantum number I? You know, nucleus possesses what? Protons and neutrons. There are some empirical rules we have. Based on that, we can give a nuclear spin quantum number by giving number of protons and number of neutrons. So there are some empirical rules to give nuclear spin quantum number based on number of protons and number of neutrons. So I am taking number of protons. Next one, number of neutrons, and nuclear spin quantum number I. Nuclear spin quantum number I. Number of protons are even and number of neutrons are also even, then nuclear spin quantum number is 0. The examples are C6, 12, O8, 16. The number of protons are what? 6, 8, even. Number of neutrons are 12 minus 6, that is 6. 16 minus 8, 8. Number of neutrons also 6, 8, both are even, its nuclear spin quantum number is 0. Such molecules are said to be microwave NMR inactive. So we may expect this type of questions. Which of the following is NMR active? Which of the following is NMR inactive? Which of the following is IR active, IR inactive? Like that. Okay. So the molecules whose spin angular moment, spin quantum number is 0, they do not possess any magnetic momentum, or they are said to be magnetically inactive. What is the expression for magnetic momentum? Mu is equal to G mu n square root of I into I plus 1. G mu n square root of I into I plus 1, but they do not possess any magnetic momentum, magnetically inactive, so they are said to be NMR inactive. Okay. Next, if you take odd number of protons, odd number of neutrons, then I value is integer. I value is integer. For example, N7 14. Number of protons are 7. Even odd neutrons are also 14 minus 7, 7 odd integer. Its I value is 1. Its I value is 1. And one more thing, deuterium, if you take H1, 2. Number of protons 1, number of neutrons also 1. Its I value also 1. And deuterium, I value is also 1. Next, if you take combination of odd and even, or even and odd. Combination of even and odd, if you take, we get off integral spin. We get off integral spin. Off integral spin we will get. For example, if you take H11, hydrogen NMR spectroscopy, proton NMR spectroscopy. Okay, H11, number of protons 1, neutrons are 0 and even. Okay, its I value is how much? And 1 by 2. F919, we have F19 NMR spectroscopy also. Its I value is also 1 by 2. Phosphorus 1531, P31 NMR spectroscopy we have. C613 NMR spectroscopy we have. In all these cases, we have combination of odd and even, number of protons and neutrons. For all these, I value is 1 by 2. For all these, I value is 1 by 2. So how to give nuclear spin quantum number? And there are some empirical rules we have. Based on that, we can give. If number of protons and neutrons are even, I value 0. That is said to be magnetically inactive nuclei. So that that cannot show NMR spectra and NMR inactive. So these two are said to be NMR active. These two are said to be NMR active. Odd integral spin, odd even or even odd, they possess off integral spin. There are some examples. If you see some more examples for spin quantum number, and for example, if you take boron 11, chlorine 35, boron 11, chlorine 35, chlorine 37, I value is 3 by 2. I value is 3 by 2. B5 10. Here B5 11, B5 10. If you take, I value is 3. Nuclear spin quantum number is 3. And now, okay, here off integral spin and odd even combination we make it. I53 127 iodine, I value is 5 by 2. Mainly you may remember these examples, and only you may remember those examples. Okay. If I value is greater than 1 by 2, such nuclei are called as quadrupolar nuclei. If I value greater than 1 by 2, such nuclei are called quadrupolar nuclei. Okay, this is the nuclear spin quantum number that we give based on number of protons and neutrons. Next, okay, which are NMR active or NMR inactive, which are magnetically active or inactive, that you may verify based on I value. If I value is 0, if number of protons and neutrons are even, that is NMR inactive. Next, what is the principle involved in the NMR spectroscopy? What is the principle involved in the NMR spectroscopy? For this, we have two approaches again. One is quantum approach, another one is classical approach. Quantum approach and classical approach. First, if you see quantum approach, okay. For example, I am taking a nuclei. For example, I am taking a nuclei whose spin quantum number is I. Whose spin quantum number is I. So whenever this nuclei is placed under the influence of magnetic field. So the definition we discussed is the interaction of nuclei with radio frequency radiation in the presence of magnetic field. What is the role of magnetic field? So its spin quantum number is not zero only. So that is magnetically active. So whenever we are placing in the magnetic field, okay, it's split into 2i plus 1 levels. Splitting, okay, lifting of degeneracy takes place. Okay, it's split into how many levels? 2i plus 1 energy levels. Okay, for example, I is equal to 1 by 2. How many energy levels will get? Number of energy levels? 2 into 1 by 2 plus 1. That is 2 energy levels we will get. Those 2 energy levels are differentiated by MIN, magnetic spin quantum number, in the presence of magnetic field. Whatever the various energy levels we are getting, those are differentiated by MI values. The possible MI values are minus I2 plus I, including 0 in integer steps. Minus I2 plus I, including 0 in integer steps. So therefore here we will get what? Minus 1 by 2 and plus 1 by 2. So it takes 2 energy levels and it's split into 2 energy levels. For example, proton, if you take proton, H1 NMR spectroscopy if you take, okay, that is also called as proton NMR spectroscopy, since in hydrogen nucleus, what about the number of neutrons? 0. Number of neutrons are 0, only one proton is present, that's why it is also to be proton NMR spectroscopy. H1 NMR spectroscopy is also called as proton NMR spectroscopy, since in its nuclei no neutrons are present, only one proton is present. Okay, if you take H1 NMR spectroscopy for proton, what about I value? 1 by 2. So it's split into how many levels? Into 2 levels. One is upward orientation, another one is downward orientation. Okay. For example, if you take I is equal to 1, it's split into how many levels? 2 into 1 plus 1. That is, it is split into 3 levels. For example, deuterium, if you take for deuterium, I value is 1. Okay, it's split into how many levels? And 3 levels. What are those 3 levels? Are distinguished, differentiated by MI values. The possible MI values are minus I2 plus I, that is minus 1, 0, plus 1. Minus 1, 0, plus 1. Like this we will get it. Okay, according to quantum approach, whenever nuclei is placed in the magnetic field, it's split into 2i plus 1 levels. Those 2i plus 1 levels are differentiated by MI values. The possible MI values are minus I2 plus I in integer steps, including 0. Okay. For example, we are taking proton NMR spectroscopy and H1 NMR spectroscopy. Okay, I am taking some protons. In the absence of magnetic field, they may arrange randomly. In the absence of magnetic field, they may arrange randomly. So we are not applying any magnetic field. B indicates strength of magnetic field. Let us consider. Okay, in the absence of magnetic field, all the protons may arrange randomly. So whenever we are applying magnetic field, for proton I value is equal to how much? 1 by 2. So it's split into 2i plus 1 levels. That means 2 into 1 by 2 plus 1. So it's split into 2 levels. Those 2 levels are differentiated by MI values. MI value plus 1 by 2 and minus 1 by 2. Upward orientation and downward orientation. For example, here I am taking 7 protons and 4 protons present with upward orientation. 3 protons present, for example, present with the downward orientation. This lifting of degeneracy is done by applying what? Magnetic field. And that lifting of degeneracy is observed by applying magnetic field. This is the role of magnetic field in recording NMR spectra. Always the population in the lower energy levels is high compared to higher energy levels according to Maxwell-Boltzmann statistics. Okay, and how to give the potential energy of the protons? The formula for potential energy of the protons is minus Gb mu n mi. Just to remember, minus Gb mu n mi. G nuclear G factor already discussed. B strength of magnetic field. Mu n nuclear Bohr magneton. Mi is magnetic spin quantum number. So E1 level and E2 level, or V1 level, V2 level. For E1 level, what we get? Mi value plus 1 by 2. So therefore, minus Gb mu n by 2 will get it. Okay. And for E2, what we will get? Already minus 1 by 2 have minus into minus plus 1 by 2 plus we will get, so GB mu n by 2. Okay. So whenever we are taking sample protons and if you place in the magnetic field, lifting of BGNS is observed. Okay. And whenever we are applying radio frequency radiation, what happens? Nucleus transitions takes place between nuclear energy levels. Okay, nuclear spin inversion takes place, flipping of nucleus takes place, nuclear spin inversion takes place. Okay. So whatever the energy absorbed during this transition, for that we will get the signal. Okay. So what is the energy gap? What is the energy gap? So delta E is equal to E2 minus E1. If you do this one GB mu n plus GB mu n by 2, 2 GB mu n by 2, and 2 gets cancelled. So we are getting GB mu n. Delta G is equal to GB mu n. So delta E is what? H nu, that is equal to GB mu n. So therefore nu is equal to what? GB mu n by H. So the radio frequency radiation frequency is equal to this frequency, then nuclear spin inversion occurs and then we may get signal. And such condition is called as resonance condition. In one of the competitive exams, this question given as what is the resonance condition? H nu is equal to GB HR, nu is equal to GB mu n by HN. If radio frequency radiation frequency is equal to GB mu n by H, then nuclear spin inversion takes place, then we will get some NMR signal. Okay. And here if you observe, delta E is directly proportional to what? G, nuclear G factor, mu n is also Bohr magneton, that is also constant. Delta E is proportional to what? Bn. So as strength of the magnetic field increases, energy gap between nuclear spin energy levels also increases, like this. This is the gap at this strength of the magnetic field. As strength of the magnetic field increases, what about the energy gap also increases. So as strength of the magnetic field increases, okay, the frequency of radio frequency radiation required also increases. As strength of the magnetic field increases, the frequency of radio frequency radiation required also increases. So this is the quantum approach, okay, which explains how we get NMR signals. So you remember the resonance condition, and H nu is equal to GB mu n, and after that delta E is directly proportional to B. As B increases, radio frequency radiation, okay, required also increases. Next one, classical approach. Classical approach. According to classical approach, whenever we are taking proton in the presence of magnetic field, already we discussed, it takes two orientations, upward orientation and downward orientation. If you take single bare proton, the two possibilities, upward orientation and downward orientation, and this proton spins. The spinning of proton is observed with respect to applied magnetic field. Spinning of proton is observed with respect to applied magnetic field. This spinning is called as precessional motion. That spinning is also called as precessional motion or Larmor precessional motion. That spinning of proton with respect to applied magnetic field or spinning of nuclei. In general, nuclei, any nuclei we can take, not only proton. Here we are concentrating on proton NMR spectroscopy. C613 also NMR active, F919 NMR active, phosphorus 1531 NMR active, all those are NMR active. Okay, so spinning of nuclei takes place with respect to applied magnetic field. That spinning is called precessional motion or Larmor precessional motion. And how many rotations, okay, it takes within a given time, and in 1 second, that is called precessional frequency or Larmor precessional frequency, that is represented by mu L. How many rotations it done with respect to applied magnetic field within a given time, that is called Larmor pressure frequency. So according to classical approach, whenever that Larmor pressure frequency matches with frequency of radio frequency radiation, then resonance condition occurs. Then we will get a signal. Then we will get a signal. This is classical approach and easy to understand. Whenever we are taking nucleus in the presence of magnetic field, spinning of nucleus takes place. How many rotations it is done within a given time, that is called precessional frequency or Larmor precessional frequency. When this precessional frequency equal to frequency of radio frequency radiation, then such situation is called what? Resonance condition. Then radiation is observed and we will get a signal. Okay, this is about classical approach. Okay, next one. So, chemically equivalent and non-equivalent protons. Chemically equivalent and non-equivalent protons. This can NMR spectroscopy. We can calculate what? How many types of protons present in a given sample. So that is useful in the structural elucidation of organic compounds. What are the various types of protons present, at which positions they are present? Okay, by using that we can give structure of organic compounds. Okay, so chemically equivalent and non-equivalent protons. If bonding connectivity is same for protons, the protons whose bonding connectivity is same, the protons whose bonding connectivity is same, they are to be chemically equivalent protons. The protons whose bonding connectivity is different, they are said to be non-equivalent protons. The protons whose bonding connectivity is same, chemically equivalent protons. The protons whose bonding connectivity is different, they are said to be chemically non-equivalent protons. For example, if you take propane and CH3, for example, I am giving like this. So this hydrogen is attached to carbon, this hydrogen also attached to carbon, but this carbon is attached to two X atoms, but this carbon is attached to two Y atoms. So bonding connectivity of these two is different. So therefore, how many types of protons we have here? Two types of protons we have. How many types of protons we have? Two types of protons we have. HA proton, HB proton, those two are chemically non-equivalent. Those two are chemically non-equivalent. For example, we have like this. Now, what about the bonding connectivity of this proton and these two protons? This is attached to carbon, which is attached to X atoms. These two attached to carbon, which is attached to Y atom. So the bonding connectivity of these two is same. So these two comes under chemically equivalent protons. Okay, and this is different. Its bonding connectivity is same. So therefore different. So how many types of protons we have? Two types of protons we have. In one set only one proton is there. In another set, how many equivalent protons are there? Two equivalent protons are there. Okay. For example, if you take propane and CH3, CH2, CH3. So these three hydrogen atoms bonding connectivity is same. So these 6 protons comes under A type, for example. These two hydrogens protons bonding connectivity is different. So those two comes under B type. So how many types of protons we have? Two types of protons we have. These 6 protons comes under one type. These 2 protons comes under another type, hydrogen atoms. For example, butane, if you take similarly, CH2, CH2, CH3. These 6 comes under same environment. These 2 comes under same environment. So A, B, B. Again, 2 types of protons we have. Bonding connectivity is same. You may check. Benzene, if you take, all 6 hydrogen atoms are same in benzene. Okay, bonding connectivity for all 6 hydrogen atoms is same. So only one type of proton we have. So if one type of proton we have, one signal we will get. If 2 types of protons are there, 2 signals we will get. So propane gives how many signals in the NMR spectroscopy? 2 signals. And since these 2 protons precessional frequency and this proton precessional frequency is different, both are in different chemical environment. Butane, if you take, how many signals will get? 2 signals. Benzene, if you take only one signal, will get. All 6 protons are same. For example, if you take ethyl alcohol, CH3, CH2, OH. Okay, here how many protons are there? All these three protons bonding connectivity is different. All these three protons bonding connectivity is different. So A type of proton, B type of proton, and C type of protons we have. The intensity of A type of protons may be more, since the signal is corresponding to 3 protons. The signal is corresponding to 2 protons. The signal is corresponding to only 1 proton. So the intensity of A signal may be more, okay, compared to B compared to C. So totally how many signals we get? 3 NMR signals we will get. 3 different types of protons we have. So therefore we will get 3 signals, and this is the concept of chemically equivalent and non-equivalent protons. Formaldehyde, if you take, bonding connectivity same. So both are what? Equivalent protons. Acetaldehyde, if you take, CH3C double bond O H, CH3CHO, if you take, these two are under different chemical environment. So we get 2 signals, okay, A type and B type. This is the concept of chemically equivalent and non-equivalent protons. Okay, so next one is shielding and de-shielding effect. Shielding and de-shielding effect. Here we are studying what? Interaction of radio frequency radiation with nuclei in the presence of magnetic field. So this is nuclei we are taking in the presence of magnetic field. This nuclei is surrounded by what? Electron cloud. This nuclei is surrounded by what? Electron cloud. Electron is also a charged particle. Okay, this is also under spinning. Whenever charged particle under spinning, it produces magnetic field. So this electron cloud also produces magnetic field. Whatever the magnetic field produced by electron, that is called as secondary magnetic field or induced magnetic field. Okay, here proton, we are studying the interaction between nucleus and radio frequency radiation in the presence of applied magnetic field. But the problem is nucleus is surrounded with the electron cloud. Electron also behaves a teeny magnet. It produces magnetic field. The magnetic field produced by electron is called secondary or induced magnetic field. So it produces magnetic field in the direction opposite to applied magnetic field. The magnetic field produced by electron is in the direction opposite to applied magnetic field. So therefore, some cancellation of magnetic field takes place. Some cancellation of magnetic field takes place. So effective magnetic field felt by the nucleus decreases. Effective magnetic field felt by the nucleus decreases. Whenever effective magnetic field felt by the nucleus decreases, its precisional frequency also decreases. Okay, some cancellation of magnetic field takes place. Then what happens? B effective decreases. B effective magnetic field felt by the nucleus decreases. We know Larmor precisional frequency is directly proportional to B. So precisional frequency decreases. Precisional frequency decreases. This effect is called as shielding effect. That effect is called as shielding effect. Now, for example, de-shielding effect. Whenever a proton is attached to more electronegative element or electron withdrawing group. Whenever proton is attached to more electronegative element or electron withdrawing group, for example HCl, okay, chlorine is more electronegative. Okay, then what happens? So the electron cloud around the nucleus decreases or not? Yes, electron cloud around the nucleus decreases since that is attached to more electronegative element or electron withdrawing group. Electron cloud decreases. Whenever electron cloud decreases, okay, whenever electron cloud decreases, the effective magnetic field may increases compared to this situation. Okay, effective magnetic field increases, precisional frequencies increases, and such effect is called as de-shielding effect. Shielding and de-shielding effect. Okay, that is related to what? Electron cloud, and simply remember like this. If electron cloud increases, what happens? Precisional frequency decreases, that is shielding effect. If electron cloud decreases, then precisional frequencies increases, that is called as de-shielding effect. Now chemical shift. Last time one question given from this chemical shift. chemical shift. Okay, so generally if you see fractional frequencies of sample protons, generally it is in the range of some million hertz or megahertz. Fractional frequencies of sample protons in the range of million hertz or megahertz. So that number is very high or not? That number is very high. Million hertz means. So in order to convert that number into small numbers, we use concept of chemical shifted. So we cannot give absolute fractional frequencies. Instead of giving absolute fractional frequencies, we give fractional frequencies by taking a reference proton frequency. What is the difference between fractional frequency of sample protons and reference proton? That difference is called as chemical shifted. Okay, generally fractional frequencies in the range of some millions. So it is difficult to handle or use such large numbers. So to convert them into small numbers, we are using a reference component. So with respect to that reference compound, we give the fractional frequencies of sample protons in small numbers. Okay, so the difference between sample protons fractional frequencies and reference proton fractional frequencies, that difference is called as chemical shift. So here we are not giving absolute fractional frequencies. We are giving fractional frequencies of sample protons with respect to reference protons. That is called chemical shifted. So chemical shift is nothing but new sample minus new reference. So sample protons fractional frequencies minus reference proton fractional frequencies, that is called as chemical shift. Okay, that I will explain by an example. And so what about the bonding connectivity of these two hydrogen atoms? Different. So this comes under A type, this comes under B type. So how many signals will get? Two signals. Two NMR signals will get. One corresponds to A, another one corresponds to B. Let us consider the fractional frequency of A proton. The fractional frequency of A proton is 60 million 60 hertz. 60 million 60 hertz on 1.41 Tesla magnetic field, and the instrument frequency 60 megahertz. On 60 megahertz instrument, and on applying 1.41 Tesla. Okay, this is the HA proton fractional frequency, and fractional frequency of HB is, for example, 60 millions 120 hertz. 60 millions 120 hertz. Okay, generally reference proton frequency is set at instrument frequency. Reference proton frequency is set at instrument frequency. So what is the instrument frequency we are using? 60 million hertz, 60 megahertz. Applied magnetic field 1.41 Tesla. So reference proton frequency is 60 million. So therefore now what is the chemical shift of HA and what is the chemical shift of HB? Chemical shift of HA, sample proton frequency minus reference proton frequency, that is 60 hertz. What is the chemical shift of HB? That is 120 hertz. Chemical shift of HA is 60 hertz, chemical shift of HB is 120 hertz. That means we converted these large numbers into small numbers by taking a reference. These are absolute fractional frequencies. But here we are not giving absolute fractional frequencies, we are giving fractional frequencies compared to reference proton. That is called as chemical shift. Okay, this is the concept of chemical shift. But the drawback with chemical shift is chemical shift depends on instrument frequency and applied magnetic field. Chemical shift depends on what? Instrument frequency and applied magnetic field. The same compound I am taking now, once again. Okay, now I am taking applied magnetic field 2.82 Tesla double. I am taking it. Instrument frequency 120 megahertz. Okay. You know, Fresnel frequencies are directly proportional to applied magnetic field. Fresnel frequencies are directly proportional to applied magnetic field. So now the Fresnel frequency of HA, we may get 120 millions, 120 hertz, and 120 millions, 120 hertz. The Fresnel frequency of HB, we may get 120 millions, 240 hertz. So now what is the chemical shift of HA and what is the chemical shift of HB? Reference proton frequency is 120 millions. Reference proton frequency is set at instrument frequency. And reference proton frequency is set at instrument frequency. So 120 millions. So if you subtract 120 millions, what will get 120 hertz? Here we will get 240 hertz. So previously we got chemical shift of HA 60 hertz, but we got 120. Chemical shift of HB 120 hertz, but now we got 240 hertz. So this is the drawback we have. If you express chemical shift in hertz, if you express chemical shift in hertz, what is the drawback? Chemical shift in hertz depends on what? Instrument frequency and applied magnetic field. Chemical shift in hertz depends on what? Instrument frequency and applied magnetic field. So to overcome this, two scales are proposed. To overcome this, two scales are proposed, ppm scale and tau scale. Chemical shift in ppm. Delta scale and tau scale, delta scale and tau scale. So delta scale. In this chemical shift we express in ppm, parts per million. In this scale chemical shift we can express in ppm, that means parts per million. So on this scale, okay, instrument frequency set at 0 ppm. Sorry, reference proton frequency. Reference proton frequency is set at 0 ppm only. After that we have like this 1 ppm, 2 ppm, 3 ppm, 4 ppm, 5 ppm, 6 and so on, like this we have. Okay. For example, if you take 60 megahertz instrument and 60 megahertz instrument, 60 millions hertz. 1 ppm indicates what? So 60 millions hertz, if you do 1 million part, 60 millions if you do 1 million part, okay, what we will get? 60 million hertz. That means 60 into 10 power 6 hertz. If you do 1 million parts, okay, 1 ppm means part per million. So if you do million parts, what will get? 60 will get. That means on 60 megahertz instrument, 1 ppm indicates what? 60 hertz. 1 ppm indicates 60 hertz. 2 ppm indicates 120 hertz. 3 ppm indicates what? 360 hertz. Okay, based on this last time one question given. If you take 100 megahertz instrument, for example, 100 millions if you do million parts, 100 millions if you do million parts, 1 part will get what? 100. 2 parts will get what? 200, like that. Okay, 100 into 10 power 6, and if you divide with 10 power 6, what will get? 100. So 1 ppm indicates what? 100 hertz. 2 ppm indicates 200 hertz. 3 ppm indicates 300 hertz. Similarly, if you take 120 megahertz instrument, 1 ppm indicates 120 hertz, 2 ppm indicates 240 hertz, 3 ppm indicates 360 hertz, like this. This is called as delta scale, in which we express chemical shift in which unit? And ppm unit. In this scale, chemical shift we express in ppm scale. Why we are expressing in ppm scale? The drawback is if you express chemical shift in hertz, that depends on both field and instrument frequency. To overcome that, we are expressing in ppm scale. Chemical shift in ppm scale is independent of both instrument frequency and applied magnetic field. It is independent of, the scale is independent of applied magnetic field and what? Instrument frequency. How it is independent of both applied magnetic field and instrument frequency, that I will explain by an example. The same example I am taking, HA type, HB type. If you take 60 megahertz instrument, okay, and 1.41 Tesla magnetic field, okay, what is the chemical shift of HA? Previously we considered 60 Hz. Chemical shift of HB we considered 120 Hz. Okay, in the previous case. Now, if you calculate in ppm, chemical shift in ppm delta, okay, the formula is new sample minus new reference by instrument frequency, new instrument in megahertz. Then we will get in ppm. This is the formula. New sample minus new reference by instrument frequency in megahertz in ppm. Or new sample minus new reference is nothing but what? Chemical shifted. Chemical shifted. Chemical shift in hertz by new instrument in megahertz. Then we will get in ppm scale. Then we will get in ppm scale. Otherwise, we can write like this also. Chemical shift in hertz by instrument frequency also in hertz. If you write instrument frequency instead of megahertz in hertz, then we have to multiply with 10 power 6. So these are the various expressions for delta scale. To calculate chemical shift in ppm scale, this is the formula we have. So for this example, if you calculate chemical shift for A type of proton and chemical shift for B type of proton, chemical shift for A type of proton and for B type of proton, what we will get? Chemical shift in hertz, that is 60 by instrument frequency is 60 in megahertz, 60. So therefore, what we are getting at 1 ppm we are getting. Okay, chemical shift in hertz by instrument frequency in megahertz. So we are getting 1 ppm. Now for B, if you see 120 chemical shift in hertz, 120 by instrument frequency is same 60 megahertz. So we are getting what? 2 ppm. We are getting 2 ppm. Chemical shift of A is 1 ppm. Chemical shift of B is 2 ppm. Okay. Now, for example, we are changing instrument frequency. 120 megahertz we are taking, and applied magnetic field 2.82 Tesla. 120 megahertz instrument and 2.82 Tesla. Whenever magnetic field is doubled, fractional frequency is also doubled. So chemical shift of HA, what we got in the previous example, once we check 120 Hz. Here chemical shift of HB, we got 240 Hz. Chemical shift of HA 120 Hz, chemical shift of HB 240 Hz. Now if you calculate in ppm scale, for A proton and B proton, what is chemical shift? 120 in Hz, chemical shift in Hz by instrument frequency. What is instrument frequency? 120. That means what we are getting? 1 ppm. For B, if you take 240 by what is instrument? Say 120. So we are getting 2 ppm. Here 1 2 ppm. Here also we got 1 2 ppm. Chemical shifts are different. Okay, whenever instrument frequency is doubled or magnetic field is doubled, chemical shift is doubled in Hz. But is there any change in the in ppm scale or not? No change. Chemical shift of A in ppm is 1 ppm always. Chemical shift of B is always 2 ppm. So that means ppm scale is independent of both instrument frequency and applied magnetic field. So that is the benefit we have with that is the benefit we have with delta scale. If you express chemical shift in delta scale, that is both independent of field and instrument frequency. And lastly, we have tau scale. Tau scale is nothing but tau is equal to 10 minus delta. Tau is equal to simply 10 minus delta. And in ppm scale, this is 0, we have 1, 2, 3 and so on we have. So if the chemical shift value is small, that is called as up field. upfield or high field. Upfield region or high field. If chemical shift values are high, chemical shift values are small, upfield or high field region. Chemical shift values are large, then that is to be downfield or low field. Downfield or low field. This is generally we will get whenever shielding effect is there. This generally we will get whenever deshielding. Deshielding. If electron cloud is high, what happens? It produces secondary magnetic field which opposes applied magnetic field. So effective magnetic field felt by the nucleus decreases. Whenever effective magnetic field felt by the nucleus decreases, special frequencies also decreases. It means chemical shift values also decreases. So whenever shielding effect is there, generally we will get signals in upfield region or high field region. Whenever deshielding effect is there, we will get signals in the downfield region or low field region. Okay, this is some introduction to NMR spectroscopy. So in the next class we will see some other concepts like what are the factors affecting delta chemical shift, what are the factors affecting chemical shift. Next, spin splitting or spin coupling. Those two concepts we will see in the next class. Okay, thank you.